With this video, we're going to run through chapter 13. We're talking about radicals. One type of radical would be a square root. And so, as always, probably a good idea to lay down the definition of a radical. We have a radical is a term of the form, and here we see this little check mark symbol with a top on it. And we, with this notation, we have an n that sits above the little check mark, and then something that sits inside. N is the index, so the index sits here above the check mark, and then it goes on to tell us that what's inside is referred to as the radicand. So if we were to talk specifically about a square root, for a square root, the index, or I sometimes call the index the root number, is 2. And so if you're dealing with the square root, you need to know that you may or may not see the 2. So if there is no 2 written for that particular radical, then it is understood to be a square root. Okay, so down here at the bottom, we sort of talk about what is a square root. And you probably already know about opposite operations such as addition, subtraction, multiplication, division. Well, square root is sort of the opposite operation of squaring a number. So if I was to say square 2, then you would take 2 and you'd raise it to the second power and get 4. If I was to ask you what the square root of 4 is, then we would write this radical symbol with a 4 inside. And since 2 is squared to get a 4, the square root of 4 is 2. And you've probably seen a little bit of this in intro. But here we're going to go a little more in depth about square roots with chapter 13. So a square root of a number a, this is just a general definition, is a number b such that if we square b, we get a. Alright, so in example 1, we're asked to explain why 3 is the square root of 9. Well, what happens if we square 3? We get 9. Therefore, the square root of 9 equals 3. Alright, it's sort of a similar argument as saying, why is 6 divided by 3 equal to 2? We just use the opposite operation to explain it. We say 6 divided by 3 is 2 because 3 times 2 equals 6. Alright, now 4 squared gives us a 16, not a 9. So the square root of 9 is not equal to 4. So whatever we square, we want to get the radicand inside. Otherwise, we're not dealing with the square root. Okay, so the square root of 9 is 3, not 4. Alright, here's a little FYI for you. Every positive real number has 2 square roots, one positive and one negative. So what they're saying here, they're just simply pointing out, for instance, if I wanted to square 2, I would get 4. So we can say that the square root of 4 equals 2. Alright, but you also have to realize that there's another number that we could square to get a 4, and that's negative 2. Okay, however, we do not want to say that the square root of 4 has two different answers. All right. We want to nail this square root of 4 down to only one answer. And so what we're going to do is refer to the positive 2 as the principal square root. Okay. So in the next comment, that's pretty much what we're talking about. 2 is equal to the square root of 4. It is the principal square root. Whereas on the other hand, negative 2 is equal to the negative of the square root of 4. Alright? And it doesn't really have a name other than the opposite or the negative of the square root of 4. Alright, so whenever you see just a square root as we do here with no negative in front, we're talking about the principal square root. So new perfect square, 25, and we're asked what are the two square roots? Well, we could take 5 and square it, and we get a 25. Or we could take a negative 5 and square it and get a 25 also. So we can say 25 has two square roots, but the principal square root is this one. Alright, it is indicated with our radical symbol and a 25 inside. So if you were to see this expression, this term, then you would respond by saying equals 5, not a negative 5. Okay, the only time you would answer negative 5 is if you were to see minus a square root of 25. In this case, the minus is on the outside, and it's waiting for us to calculate this portion of the term. So we would write square root of 25 is 5, but then we have a negative in front, so our result is a negative 5. Okay. So we have to be a little bit picky about our when we talk about radicals, specifically the square root. Now we're going to point out something else about square roots that is sort of a nuisance. We cannot have a negative number inside of a square root symbol and expect to get a real number out of that. So we said square root of 4, or in this case square root of negative 4, just the square root, is asking us the question, what do we square to get negative 4? Alright, when you see this term written this way with the radical, this is what you're being asked. What do we square to get a negative 4? Negative 4 is the number inside. Well, the answer is there is no real number that we can square to get a negative 4. The only possible way to get a 4 is to use the number 2 or its opposite, negative 2. So if we square the 2's, we'll definitely get a 4. But when you square a positive number, you get a positive number back. Likewise, even if we use a negative 2, when you square a negative, you have a negative times a negative. You have to apply the double negative rule. You still get a positive 4, not a negative one. So we only want to consider real numbers, and 2 were the only possible real numbers that could give us the answer, but they end up being positive, so, and not negative as we have in the radicand. So there is no real number that we can square to get negative 4. So in this case, out to the side, we would just say this is not a real number. All right. Now here we have this starred comment, and we're trying to define um, or talk about what we do when we take the square root of a variable expression, as in this case, the square root of x squared. Okay, what we want to do is just say x, but there's a catch to writing it this way. If we write just square root of x squared equals x, then we have to go ahead and say that x cannot be a negative number, or we just say x is non-negative. All right, why is that? Well, if we look at this starred comment up here, and we look at square root of 4, in both cases, for instance, on one hand, we could have a 2 squared inside the radical. If we square a 2, then we get the square root of 4, which we know is equal to 2. All right. So what we're doing is we're following our template of square root of x squared equals x. Okay. If I just plug in a 2 here and square it on the inside, and then I put a 2 in the place of this x, we don't run into a problem. Okay, we've already said that, well, 2 squared on the inside of the radical is 4, and the square root of 4 is equal to 2, so this checks out. Okay, the positive 2 doesn't cause problems. But on the other hand, if we say that x equals a negative 2, and we plug it into our equation for the square root of x squared, then what we get on the left is a negative 2 squared inside the radical, and then we replace this x with a negative 2 also. Alright, the left side, negative 2 squared, ends up being a positive 4. But now the right side is still a negative 2. There's nothing that we can do about that. And basically what we're saying here is that 2 equals a negative 2, because this radical is referring only to the principal square root. Alright, so we run into trouble with variables when we're dealing with radical symbols, and what we're going to say for the remainder of this chapter is that we're only going to deal with x's or variables that are non-negative. Otherwise, we'll have to apply these absolute value bars around our result in the way of variables. Alright, so what we see here are a couple expressions, radical terms that were simplified for us. And one way you can look at this is just to simply separate these into a square root of 25 and then a square root of x squared. We already know what the square root of 25 is. The principal square root is 5. And then if x, as long as x is a non-negative, we can replace this square root of x squared with an x. and so we see that the result is a 5x. You simply just go through each factor of the product inside and take the square root of each individual piece. Now, that's if you're dealing with a single term. If we look over here to the right, for this radical, we have an x plus a y, but this is squared. Alright, so what we have is something squared inside of a radical. So whatever's squared ends up being the square root. And so that doesn't have to be a single variable or a single number. It can be, as we see here, the sum of two. Okay. All right. Now, when I say sum, I don't want you to believe that, as an example 4, that you can break up a sum from inside the radical. We cannot separate the 9 and the 16 into separate radicals. Okay, as you should see here, there's a does not equal sign in between these two expressions. So, uh, real simple. If we wanted to verify this, on the left-hand side, we could simply add the 9 and the 16 to get a 25. And as we saw before, the square root of 25 is 5. Back on the right side, if we were to just calculate this expression, the square root of 9 would give us a 3, and the square root of 16 would give us a 4. However, when we add 3 and 4, we get a 7 and not a 5. So this is not a legitimate way to break up a sum. You cannot break up sums and differences inside the radical into two or more separate radicals. Alright, however, if you have a product, for instance, if we have factor 1 and then we have factor 2, and all of this is multiplied, and maybe factor 3, this is the product. We can separate these into separate square roots in this case. But these three separate square roots would simply be multiplied by one another. Alright, they're just simply not under the same radical anymore. Cannot do that with sums and differences. Alright, down below we have some square root terms that we want to simplify. And again, we're only considering variables with that are non-negative, that represent non-negative numbers. So we don't have to worry about absolute value bars. Example 5, we could write this as the square root of 49 times the square root of x squared, and think about each part separately. But in the end, what we get is a 7 and an x. For example 6, we already have a negative on the outside of the square root. If we wanted to, we could break apart the 9 into y squared. Not really necessary, but you could if you wanted to. And then we still have the negative. You don't want to just drop it. The square root of 9 is 3, and then the square root of y squared would be a y. Now, for example 7, as I said before at the beginning of this page, you cannot separate the x squared, 4x, and 4 into separate radicals. What we do in this case is we use what we learned from the previous chapters and we write this, we break this trinomial up into its factors. So once things are multiplied inside the radical, we can break it up if we need to. X squared plus 4x plus 4 turns out to just give us 2x plus 2's. This can be rewritten with an exponent, x plus 2 squared. Now, another way to look at a square root, okay, the root number here is 2. It's not necessary to write it, but you'll notice that the root number matches the exponent inside. So what the root number tells us is that if we have 2 of one factor inside the radical, then we can bring one of them out front. So here we have 2x plus 2. So to simplify this radical, I just bring one of them out front. So the square root of x squared plus 4x plus 4 is x plus 2. If you want to, you can take the radicand inside and factor it, such as in the case of 64, we could factor that as an 8 times an 8. We could break apart the perfect square numbers. Alright, then we could interpret m squared as an m times n. So there's several different ways to look at radicals. You just have to go with what works for you. Now, this 8 times 8 and m times m, we could look at it as an 8 over m times an 8 over m. And so what we have inside the radical is an 8 over m squared. Alright, and we just got through saying that if we have 2 of a factor inside and we're dealing with the square root, then we can take one of them out. So we bring one of these factors outside the radical. We've used up these two, and so our answer is 8 over m. So there's probably a few different ways that you could see a radical term simplified. So another type of radical that you've probably already dealt with would be a cube root. And a cube root is simply our radical symbol with the number 3 as our index. Alright, so we go through a lot of the same arguments that we did with the square root, except now we're dealing with the cube root. So example 9 wants us to explain why 3 is a cube root of 27. If we take 3 and cube it, then what we have here are 3 3's multiplied. 3 times 3 is 9, and then we have an additional 3. 9 times 3 is 27. So if 3 squared equals 27, then the reverse operation, the cube root of 27, would simply just give us back to 3. Well, why is 4 not the cube root? Okay, so y is the cube root of 27 not equal to 4? Well, it's real simple. If we cube 4, we get 4 times 4 times 4, 16 times 4, and it turns out to be a 64, not a 27. So we cannot say the cube root of 27 is 4. That number is 3 only. Alright, so here we have a little comment about cube roots. When we talked about square roots, we said that there were actually 2 square roots for every number, but we sort of focus only on the principal square root in this chapter. Now for cube roots, there are actually 3 for each number. 2 of them are what we call complex numbers that we haven't talked about yet, so we're going to save that for a later chapter. But the 1 is our real number. So on the previous page, we said the cube root of 27 equals 3. This is our only real number result of the cube root of 27. There are actually 2 other numbers, but they are complex numbers. We want to focus on the real numbers. Alright, so here we have a second comment about cube roots, and what they're trying to point out to us is that we don't run into the same issue with variables as we do with square roots. So let's take a look at this expression that we're given, the cube root of x cubed. Alright, we can just go ahead and say that this is equal to x without having to worry about putting bars around this x here. And x doesn't have to be restricted. It can be positive or negative. So what I'll do is I'll use an example of 2 and negative 2 as I did with the square root. If we say x equals 2 and we replace the x inside with a 2, and then over here on the right side of the equation we replace that with a 2, then what we get on the left is a cube root of 8, and it's equal to 2. Okay, everything checks out here. If I raise 2 to the 3rd power, I get the 8, so the cube root of 8 is 2. Now, does this expression, or this equation here, I should say, does it hold if I let x be negative 2? If we put it in the radical and cube it, and then I replace the x on the right side with a negative 2, then we see we're taking the cube root of actually a different number. We're taking the cube root of a negative 8 and not a positive 8. So we can get and should get a different result. So the cube root of negative 8 does equal a negative 2. If you take a negative 2 and you cube it, it would be the equivalent of having 3 negative 2's multiplied. 2 times 2 times 2 gives us an 8, and then if we have an odd number of negatives, we get a negative 8. So we don't run into this issue of ending up with the same number inside the radical. We can have different answers. So no need, and that's the main takeaway here, there is no need for absolute value bars when you're dealing with a cube root or any other root number that is odd. So with cube roots, we are allowed to have negatives inside, and the way you can consider yourself dealing with that negative is just simply taking the negative and putting it outside of the radical. Okay, so here we have 3 radical expressions that are simplified for us. The cube root of 8 would give us a 2, and then the cube root of x cubed would give us the x. So our result here is 2x. This negative simply jumps to the outside of the radical. The cube root of a 64 equals the 4, and then the cube root of a y cubed gives us the y. So we just put all our pieces together, the negative, the 4, and the y, to give us the result. And here we see that we have 3 of these factors inside the parentheses. It wouldn't matter what was inside these parentheses. If I have a radical expression, cube root of something, it doesn't matter what it is, cubed on the inside, then I'm simply just going to write our answer as whatever is on the inside. And in this case, that worked out to be an a plus b. Alright, so here's 3 more that we can simplify. If you want to, you can break this product inside apart into a cube root of 125 and a cube root of x cubed. But in the end, we get a 5 and we get an x. The negative, we can simply just take it out of the radical and put it in front. A cube root of a 27 is 3, and then the cube root of y to the third would just be a y. You can think of yourself as dividing this exponent 3 by the root number 3, and what you get is a 1. So on the outside, we write y to the first power. Or you could just simply write a y. Alright, here's another situation where we have the cube root of something, doesn't matter what it is, raised to the third power. Well, what we do is we just take what's inside these parentheses and write that out as our cube root, 2a minus 3b. So how does this carry on with bigger and bigger root numbers? And what they're saying here is that we could have root numbers of 4. We could have a 5th root. We could have a 6th root. We could have a 7th root, and so on. Okay, these root numbers can keep going. Alright, but the idea is the same. If we're talking about a 4th root, then we just say, what do we raise to the 4th power to get the number inside the radical? For a 5th root, we say, what do we raise to the 5th power to get this number inside the radical, and so on. So in example 13, they want us to explain why 2 is the 4th root of 16. Well, 2 to the 4th power is a 2 times a 2 times a 2, 4 2's multiplied. Each pair of 2's gives us a 4, and 4 times 4 equals 16. So the 4th root of 16 equals 2. 3 is not the 4th root, because if we raise 3 to the 4th power, each pair of 3's would be a 9, and a 9 times a 9 is an 81, and that does not equal the number, the radicand of the 4th root of 16. Okay, 81 is not 16, so 3 is not the cube root. Okay, what these comments above are talking about is that in this course, we're pretty much just concerned with the real roots of a number. Turns out there's more roots than that of any particular radical expression, but we're only concerned with the real ones. So our definition, we're talking about when we say real, we're talking about the principal nth root. So if if we're dealing with an even root number, then and you see only the radical expression, such as in the case of the fourth root of 81, then you should know that you would just give us the positive fourth root. In this case, we're dealing with an index of 4, so we're talking about fourth roots. You should return the principal. This other version, if you needed to return a -3 instead of a positive, the principal root, then you would see this negative sign in front of the radical. Now, when you're dealing with odd index numbers, then that's not an issue. So, what we'll do is we'll look down here and we'll simplify these expressions. Example 14 and 15. What do we raise? We could pose this as the question, what number is raised to the 7th power to get 128? Alright. Well, your calculator may or may not have a 7th root button. Okay. There may be a button or a function in your calculator where you have the nth, you have an n here above the radical symbol, and when you hit that, it just allows you to change this n to whatever index you're dealing with. Okay, you may have this in your calculator, but should you not have that, then I want to go ahead and tell you how you would calculate this if you weren't familiar with the numbers 128. Okay, of course you could start just simply taking numbers like 2 and raise it to the 7th, 3 and raise it to the 7th, 4 and raise it to the 7th, but that can work out to be quite a bit if you have a big number inside your radical. It turns out that 2 to the 7th is actually 128, but I just want you to be aware that you could rewrite the 7th root of 128 as simply a 128 raised to the 1/7th power. Okay. Just to pick something random, let's say we had the 9th root of 1077. This is not going to work out to be a nice whole number, but if you wanted to calculate this and you didn't have this special nth root button in your calculator, then you would just write 1077 and you would raise it to the 1/9th power. It would give you the same result. Alright. So, the 7th root of 128 is 2. We return the positive number, the principal square root. This one could be a little tricky if you weren't careful. What we want to do is just simply carry this negative over that's sitting out front, and we want to concentrate on the rest of this term. So the 5th root of minus 243. If you wanted to, you could rewrite this as minus 243 to the 1/5 power. Alright, so without knowing that, you'd pretty much just have to say 2 fifth power, 3 to the fifth, and 4 to the fifth, until you ran into one of these that actually gave you 243. And 3 is actually that number. So 3 to the fifth is 243. If we want a negative 243, as we have in our expression here, then we're going to have to make this 3 a negative. Okay, so this part, just the fifth root, the radical part, ends up being a negative 3. The other negative is just going to sit in front of it, and to finish the problem, we just invoke the double negative rule and say, overall, this ends up being a positive 3. Okay, because we had the negative on the outside waiting for it. Minus minus 3 is a plus 3. So be careful with the negative signs. Okay, in this next part, if you pick up on, I guess you could call it a pattern, um, here you see the root number, the root or index number equals the exponent of the variable inside. So if the index matches the exponent, then we just simply take the base and write that as our nth root. Alright, so the fourth root of x to the fourth is just the x. The 5 and the 5 match, so we just write out a y. We write out the base. One you want to be careful with is if you have an even root number and there's a negative inside, you just simply write out not a real number. Alright, we don't try to compute this because we haven't talked about complex numbers yet. However, if the root number is odd, such as the 7th root, then we just simply take the negative to the outside and we say 7 divided by 7, or this 7 divided by that 7 is 1. So out front, we just write a y to the first power. We just take the base. If the index matches the exponent, you just take the base. In this case, we had a negative that tagged along with it. And the negatives are okay when you're dealing with odd index numbers. You can just simply take them out of the radical. So shouldn't think about this too much. 8 matches the 8 exponent, so the answer's x. Here, the index matches the exponent, so we write the base y. 10 matches the 10. 10 is the exponent of x plus y, so our answer is x plus y. Here we have a negative inside the radical, but the index is odd. It's an 11. So the negative is okay, and we take the base of the exponential expression. The 11 matches the 11, so we end up with a negative z. Here we have a negative inside a radical, but the index is even. So when you have a negative and an even index, we say that this radical is not real, not a real number. Now we're going to talk about what the graph of this parent function looks like. And always, when you run into a new type of function that you've never seen before, what you can do is construct a table of values. In that table, you would have a column or a row for each variable. So for this parent function, we have y and we have x. So we have a X row and a Y row. And what we want to do is pick values for X. And one thing that we already know about a square root is that we cannot put negative numbers in underneath the radical. Okay, and we're talking about a square root. So notice here in our table that's already worked out in our workbook that we have no negative numbers. We've only used positive ones. The square root of a negative number would not give us a real number for y. So we have 0, 1, 2, 3, 4, 9, and here we've just simply put those numbers in the square root and calculated it. Now, what we would do with this table is go down here and plot these XY pairs, and if we were to do that, you would see that they would all fall on this line. So if you ever run into a function that you don't remember what it looks like and you have no graphing calculator, then you would just make a table of values for X, compute the Y values based on the X's that you chose, graph those XY pairs on the coordinate plane, and then connect the dots. So if we did that, we would see that our square root function simply looks like this, as we have at the bottom of the page. Now, we were restricted as far as the X values that we put into our function, our square root function. So already you should know that the domain of this function is 0 or any number above that. It's either 0 or any positive number. That would be our domain. Okay, so in other words, this square root function casts a shadow on the positive X axis. Alright. Now, what about the range? Alright. We want to know what Y values. Okay. What Y's are we going to get out of this function? Well, you can just figure that out by simply looking at this picture. Now, this square root function looks like it sort of flattens out. Okay, and it gets to a point to where it won't go any higher. But that's just the looks of things. This square root function, if we pick, and you can verify this with your calculator, if we pick bigger and bigger numbers, so if I picked square root of 1,000 and then square root of 1,000,000, I'm going to continue to get back bigger and bigger numbers. So the bigger the number that I choose for X, the bigger the number I'm going to get for Y. So what I'm trying to say here is that this square root function continues to increase. Not very fast, but it will continue to go upward. Now, if you look at down here below, it gets to 0 and it stops. It doesn't go down here below the x-axis. So for the range, we also say it starts at 0 and goes up to positive infinity. These are the only y values that we can expect to get out of this square root function. So over here, maybe we could write bigger y's as x increases. Alright, and it will not hit a limit. It'll go all the way out to positive infinity. Now, through the next few pages, we're going to do something similar to what you've already seen. In a previous chapter, we talked about y equals absolute value of x, absolute value functions. And what we did with those is we graphed transformations of this parent function, y equals absolute value of x. If you were to graph that, we said in a previous chapter that this looks like a V. Alright, just the standard absolute value of x. Now, if we were to change it slightly and instead write absolute value of x minus 2, then what this is going to do with the minus 2 outside the absolute value bars, this is going to move our parent function, this black curve, down 2 on the y-axis. So instead of starting here at the origin, we're now going to start here down at negative 2, and then we'll simply copy down our parent function starting at this new point. Alright, so numbers outside the bars in the previous chapter, we said they shift the parent function up or down. One other transformation that we talked about was a horizontal one, and for instance, we could write absolute value of x and put the minus 2 inside the bars. The effect that this minus 2 has on the parent function, this black curve is our parent function. The effect that this negative 2 has is it moves it over to the right now. And there is where we start our absolute value function. It just forms a V, okay? And the sides break off at 45 degrees. Alright, so if we have a number that's situated inside the absolute value bars, then it's going to shift it left or right. Alright, I remind you of all of this because this square root function is going to work the same way. On the previous page, we talked about just a basic parent function y equals square root of x, and we said that it is going to look, it's going to start at the origin, and it's simply going to veer off and sort of flatten out to the right. Never gets completely flat, we talked about that, but it does look as if it's going to become flat. So here is the basic picture. If we were to perform the same sort of transformations as we did over here on the absolute value function, we could write square root of x and then a minus 2 on the outside. It's going to have the same effect. It's going to move square root of x down 2 on the y-axis, and this will become our new starting point, and we'll simply copy this parent function in its new location. If we were to put the negative 2 now inside the radical with the x, then the effect the negative 2 will have now is it will move it over to the right, just as it did to the absolute value function. So we move to the right from the origin, it shifts over, and then we just copy down our same parent function in the new location. Alright. So hopefully you picked up on that the first time we talked about it. But on this page you can see what we're graphing is y equals square root of x minus 3. And so this negative 3 has the result of moving the parent function over 3 units to the right. 1, 2, 3. And then we just copy down our square root of x. Alright, now we've shifted this to the right. And when we shift a function to the right, sometimes we can change the possible x values that are allowed inside this function with respect to the parent function. So before we started, our first value that we could put into the square root of x was a 0. But now, if we put a 0 inside of the square root of x minus 3, we get the square root of negative 3, and it's not real. So that's just to say that our domain isn't the same as it was on the previous page when we just had the square root of x. We now have this minus 3 there, and it's going to shift our domain to where the first number that's allowed in the x is 3, and any number after that is legal. Okay. So if we shift it left or right, you can mess up, or you can change your domain. Now for the range, this parent function square root of x hasn't been shifted up or down. So typically when you don't do that, it doesn't change the range. So that is still the same as the previous page, 0 to infinity, bracket for 0. Okay, here is another type of transformation other than horizontal or vertical. We have a negative sign in front of the square root of x. So, just to remind you of our parent function, square root of x, the square root of 1 is 1, the square root of 4 is 2, and so our function is going to look something like this. Hopefully you can draw a little bit better curve than I can, but this is pretty much what the square root of x looks like. Now, when we had a table, we said the square root of 1 was 1, the square root of 4 was 2, and the square root of 9 was 3. Alright, and if we kept going, I'd probably cross through 3 out here somewhere, maybe right about there. Now, if we look at the table for the negative square root, we can use the same x values, 1, 4, and 9, and we want to use positive x values because we're putting these numbers still inside the square root. And so this negative square root of x is still going to be over here on the right portion of the x-axis. But now, instead of getting just a 1 for the square root, we place a negative in front of it. Square root of 4 is still 2, but we have a negative in front of it. So the negative in front of the parent function simply changes the sign of all of our y values in our table. And so what that does for each of these points is it rotates it down, it mirrors it across the x-axis. So 1 becomes a negative 1, 2 becomes a negative 2, 3 becomes a negative 3. So in other words, a negative in front of the square root of x flips, and maybe I should have done this in a different color. It's going to flip our parent function, the square root of x. It's going to flip it down below the x-axis. Now, we didn't shift it left, right, or up or down, but we have altered the y values. So when we go down here and we're asked to list the domain and the range, our domain stays the same, 0 or positive numbers for x, and our range becomes the negative portion, since we flipped it across the x-axis, becomes the negative portion of the y-axis. So we start at negative infinity and we go up to 0. We don't start at 0. Alright, for this last bit, you could say the graph of negative square root of x is simply square root of x flipped, or mirrored across the x-axis. Alright, our last function here, square root of x plus 3. We have the number is inside the radical, and so that moves it left or right. And the way you tell whether it's one way or the other is left is going to be positive and minus is, left is going to be positive and right is going to be negative. Okay, and so obviously we're dealing with a positive number here, plus 3, so we're going to move it to the, we're going to start at the origin and we're going to move it 1, 2, 3 to the left. So this number, when it's inside the parent function, is sort of counterintuitive. If you go to the left of the origin, you run into negative x values. Okay, but when the number is positive, you actually go to the left. Alright, so this is where our square root function is going to start, and at this point we're just simply starting in this new location and drawing our square root of x function. Okay, it's going to pass through this point. If we go over 1, then we go up 1. If we go over 1, 2, 3, 4, then we go up 2. Having a little trouble drawing this neatly. Okay, so we're starting at negative 3. If we go over 1 and up 1, that would be our first point. Then if we go over 4, then we go up 2, and that should get us started. So I'll try to draw a smooth curve through these points. And you could go out 9 and then go up 3 at some point over here, which I think would fall right about there. So it doesn't have to be perfect. You just want it to be somewhat accurate with the points. You definitely would not want to do this. This would be wrong, so I'm going to put it in red. It's great that you can find your starting point, but then don't just draw a curve that's off to the right. This would not be the square root of x plus 3. It's too high. Your values that you pass your curve through need to be somewhat reasonable. Alright, what about the domain? Well, we shifted it to the left. So we're going to pick up more values of our domain. With respect to x, the function now starts at negative 3 and veers to infinity toward the right. The range, we didn't shift it up or down or flip it, so we're just going to have the same range as our parent function, 0 to infinity. How are the graphs related? I just simply say shifted 3 units to the left. actually have one more that we need to work out. We still have a plus 3, but it is outside the parent function. So it moves it up or down. Okay, and in this case, the signs are intuitive. Down, you usually associate with negative, and up, the positive sign. So, with us having a plus 3 here, we would start at the origin where our parent function starts, and we would go up 1, 2, 3 units. So instead of starting at the origin, we would simply start right there. And so it only shifts the parent function up 3. From this point, we just draw an exact copy of the square root of x. Okay, so the only part that really needs to be graphed here is this curve that veers off to the right and up. Alright, so at the bottom, it wants us to talk about the domain and the range. So, with respect to this, which is just the parent function, square root of x, have we shifted it left or right? Have we changed the x values that we're allowed to put inside the square root, or not this square root, but this function y equals the square root of x plus 3? And the answer to that would be no. We didn't shift it left or right. So our domain stays the same. The curve still overshadows this positive portion of the x-axis. Okay, so it casts a shadow on this part all the way out to positive infinity. Now for the range, we did shift it up with respect to the parent function. So if we were to apply the horizontal line test, our first value of y would land right here at positive 3. And then our horizontal line test would only pass for values above positive 3. If we draw a horizontal line below that, we never intersect our function. Okay, so these numbers on the y-axis are not included in the range. So the first value of our range would be a plus 3, and it would continue out to infinity. Alright, and finally we have an application problem. Make sure you look at the example above, but I'm just going to go ahead and work out this last one, example 24. It's the same type, and what happens here is we're given a formula, and it tells us s equals 4 pi r squared. This is the formula for the surface area of a sphere. Alright, now it's set up to calculate s if we're given the radius of the sphere, but we're not given the radius. Okay, we're given the surface area. We're given the s, and we want to solve for the r. So what we need to do is take this formula and rearrange it to get the r by itself. And you can see here that the r is squared. And whenever that happens, you're going to have to apply a radical. Alright, the first step toward getting the r by itself would be to divide both sides by 4 pi. Okay, can't simplify the left side, but we do have the 4 pi's cancel on the right, and we're left with r squared. Alright, we want r by itself, and it has this square. The opposite of a square, operation of square, is square root. It's sort of like multiply and divide are opposite operations. Add, subtract are opposite operations. So if we have a square that we want to get rid of, we have to apply the square root. So what we'll write here is the square root of the right hand side and the left hand side. Now, we're only going to consider the principal square root, and we're only going to consider positive values of our radius. You don't talk about distances and lengths as negative numbers. So r is going to be positive, and over here on the left, and we can drop that 2. Okay, this radical and that exponent 2 knock each other out, and so we're just left with r on the right. And here we have our expression that's set up to calculate our radius. Now, we take our 196 pi and we replace s. So this becomes a 196 pi over a 4 pi. You can carry out any operations as you normally would inside the radical. The place where you want to be careful is when you want to start taking things out of the radical to the outside. Now, like I said, on the inside, we would just say pi divided by pi, those cancel out. And so we'd be left with 196 over 4. And we can divide these two numbers inside the radical. 196 divided by 4 would be a 49. Now, luckily we ended up with a perfect square. The square root of 49 gives us a 7. And this is what our radius works out to be. So, radicals, since they're opposite operations of squares, they really do have an application to real-world situations. There could be a real-world situation where you needed to know the surface area of a sphere, or as in the example above, the volume of a particular object. And to fully work with that formula, you have to understand radicals, and you have to know how to simplify them. So that's it for this chapter. Thanks for watching.